Okay, in this video, we're going to continue with problem set 12 from Calc D, my multivariable class, and we are going to be using Green's theorem, and we're going counterclockwise unless otherwise stated. I think we're going counterclockwise in all of these, but let's find out. Problem number 3, we're doing the line integral y squared dx plus x squared dy over the unit square, which goes 0 to 1, 0 to 1 for x and for y. All right, so we're doing this line integral. So we are going to have our bounds for x goes 0 to 1, for y goes 0 to 1, and then we need to know what f1 and f2 are. So I like to identify them. So we have y squared comma x squared is our vector field. So we're going to do partial x of f2 minus partial y of f1. I'm going to set that up. So we have this, partial x of f2 minus partial y of f1. Now we just simplify that integrand, right? Like find those partials. So that'll be 2x minus 2y and dy dx. And now we're actually just going to integrate. So I'm going to do integrate with respect to y. So I will get 2xy minus y squared. And then y is going from 0 to y is equal to 1. And then dx. So when we sub in 1, we get 2x minus 1. When we sub in 0, everything zeroes out. So now we're just doing the integral from 0 to 1 of 2x minus 1. Plus 1 times the reciprocal, so we get this. Plug in 1, you get 1 minus 1. Plug in 0, you get 0 minus 0. This gives us 0. All right, so that's Green's theorem. It's a quick way of evaluating line integrals when it applies, right? So you have to have that like closed region that you're integrating over. All right, so number 4, we're going to do the line integral of e to the 2x plus y dx plus e to the negative y dy. Our curve is going to be the triangle, or our path, I guess, 0 to 1, 0, 0 to 1, 0 to 1, 1. All right, so let's set it up. So our line integral, we got to draw this, I think. So if you draw it, you have this. Our region is that triangle right there. So if you look at it, x is definitely going from 0 to 1. And then y likes to go from bottom to top. So if we go bottom to top, that's going from 0 to x. So I always like to draw those arrows, set it up. Those will tell us our bounds, right? So x goes 0 to 1, y goes from 0 to x. Now I need to know what f1 and f2 are. If we look up here, f1 is always going to be with dx and f2 is always going to be with dy. Make sure you don't get tricked by that, right? Because sometimes f1 is 0, so you only have dy, and sometimes f2 is 0, so you only have dx. Really got to pay attention, make sure you're doing the right thing. So we'll have partial x of f2 minus partial y of f1. Now we're just basically doing it. Partial x of f2, because it's just e to the negative y, is going to be 0. So this actually simplifies quite a bit to 0 to 1, 0 to x, 0 minus e to the 2x plus y, dy dx. Integrate negative e to the 2x plus y dy, and we just get negative e to the 2x plus y. So that'll be this, where y is going from 0 to x, right? So I like to, again, always say what I'm subbing in for because I get easily confused. Maybe you don't. If you don't, then you don't have to do that. So I'm going to plug in x for y, which gives me negative e to the 2x plus x, so negative e to the 3x, and then minus, plug in 0, I get negative e to the 2x. So minus negative is plus, that gives me the integral from 0 to 1, negative e to the 3x minus negative, so plus e to the 2x dx. Now we just integrate these. I don't know, use substitution, or you just look at it and balance it out. I have negative 1/3 e to the 3x plus 1/2 e to the 2x. We're going from 0 to 1. When you plug in, this is going to be ugly. When you plug in 1, you get negative 1/3 e cubed plus 1/2 e squared minus, when you plug in 0, you get negative 1/3 plus 1/2. If you simplify this, you could probably maybe leave that. It depends on the class that you're in. If you simplify that, I'm pretty sure you get 1/3 e cubed plus 1/2 e squared minus 1/6. All right, let's take a look at another one. The line integral of x squared y dx. So this is kind of the scenario I was talking about where it looks like f1 is x squared y because that's with dx, and it looks like f2 is 0 because there's nothing dy. So you got to be on the lookout for that because that is definitely a trick question you can run into. All right, so we're doing this. It's going to be the double integral over whatever our domain is. We're doing f1, again, is here. f2 must be 0 because there's no dy. So we're going to do partial x of f2, which is still just 0, minus partial y of f1. And then that'll be dA, and we're going to work that out in a second. Unit circle, right? So since it's a unit circle, I'm thinking we should just use polar here, which means that r goes from 0 to 1 and theta goes from 0 to 2 pi. I'm going to do dr d theta. I pretty much always do dr d theta. So theta's on the outside, r's on the inside. And then x is going to be r cosine. So we get negative r squared cosine squared. And then dA is going to be r dr d theta. So don't forget, like all the polar things that you know still apply once you're doing the double integral. Once you've set it up and you're doing the double integral, these are like just straight up normal double integrals. You just figure out the best way to do them and you go for it. This we can separate into two separate integrals because it's a product of like f of r and g of theta. So we can separate it. I need to integrate cosine squared, which means that I'm going to replace cosine squared with 1 plus cosine of 2 theta over 2 using a double angle formula or a power reducing formula that comes from the double angle formula. And then the integral of negative r cubed is negative 1/4 r to the 4th. That's going from 0 to 1. And then we still have to like do the integral for theta. So that's going to give us 1/2 theta and then minus 1/4 cosine, nope, 1/4 sine of 2 theta. So we'll get this from 0 to 2 pi. And then that part just evaluates to negative 1/4. Plug in, so the sine of 4 pi is 0. The sine of 0 is 0. So all that's really happening here is the theta stuff. 1/2 of 2 pi is pi, and then 0, obviously. So we're just going to end up with pi minus 0, and then minus 0 times negative 1/4, which overall is giving us negative pi over 4. All right, I'm going to do one more in this video. So let's see. We've got line integral FDR. F is given explicitly this time as x plus y comma x squared minus y. So again, we're going to identify f1, f2. They're just in order. Our boundary or our curve is going to be the boundary of the region that has y equals x squared, y equals the square root of x, and x between 0 and 1. Okay, so that's what our region kind of looks like. If we go from left to right, we go from 0 to 1. I mean, they told us that. Y likes to go from bottom to top, so I like to draw that arrow. The bottom curve here is x squared, and then the top is going to be the square root of x. So now we know our bounds, right? It's going to be 0 to 1, and then x squared to root x. So let's set this up. So our line integral that we're doing is going to be the integral from 0 to 1, and then x squared to root x of, we got f1 and f2. So it's going to be partial x of f2 minus partial y of f1. So partial x of f2, which is x squared minus y, minus partial y of f1, which is x plus y. They're very algorithmic once you like get into it. They're very intimidating before you know what to do. But Green's theorem is pretty straightforward. I'm sure that somewhere out there they're asking incredibly hard Green's theorem questions, but like most of the ones that we deal with are pretty straightforward. All right, let's clean up this integrand by actually finding the partial derivatives. So partial x of x squared minus y is just 2x. Partial, that should say partial y rather of x plus y. That's I wrote that wrong, right? So that's just going to be 1, so 2x minus 1. And then we're going to integrate with respect to y, which just introduces a y, right? Because there's no y in this thing. So we end up with integral 0 to 1, 2x minus 1 times y, where y is going from x squared to root x, and then dx. Okay, so this will look ugly, and I'm just going to do it. So we have the 2x minus 1, and then when you sub in root x, that's x to the 1/2. When you sub in x squared, that's just x squared. I'm going to expand this. This is like an annoying this is an annoying algebra 1 problem, but then it becomes an annoying calc 1 problem. So I've expanded. I'm going to reverse the power rule every single time. So I get this, and then when I plug in 1, I get 4/5 minus 1/2 minus 2/3 plus 1/3. When I plug in 0, everything goes away. So I end up with this, and if you simplify it, you get negative 1 over 30. All right, I'm going to stop this video here. I'll be back in the next one to, I think, finish this problem set. So I'll see you there.